This video is an introduction to bonding and nomenclature, starting with the octet rule and ions. So the octet rule is one of the most important factors in the way an atom behaves, both chemically and physically, is its number of valence electrons. And, it wants to get to 8 valence electrons due to the octet rule. So if we look, it's no coincidence that there are 8 of these main groups on the periodic table labeled 1 through 8. There are 8 of them because of this octet rule, right? Oct for 8, like octopus has 8 legs. If we're at, let's say, principal quantum level 2. Okay, so if we're at any of these elements, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, that are principal quantum level 2. And we want to write one of their electron configurations. Let's just say carbon. We would start here and we would fill carbon's 1s with 2 electrons. And then we would get down here and we would fill 2s1, 2s2. Okay, so we'd be at 2s2 electrons. Okay, so carbon has 1s, 2, 2s, 1 and 2 electrons, and 2p, 1 and 2 electrons. 2p, 2 total, 2p electrons. The valence electrons were those final s and p electrons, the s2 and the p2. Now, at the 2 level, at principal energy level 2, we could have fit a maximum. There were a max of 2s2 and 2p6 electrons for a total of, let's even just write it with a different color, 2 plus 6 is our 8 electrons. That's where we get our octet rule, right? We can get a maximum of 8 total, valence electrons max, because that's the amount of electrons that we can fit in total in s and p orbitals. And it's our s's and p's that are our outermost valence electrons. So with carbon, it only has, 2 electrons in that 2p. So it has this partially filled valence shell. Get to oxygen and it will have 2p4, and fluorine will have 2p5, and neon, finally 2p6. Finally, in neon, we have S2 and P6 for 8 total electrons. Now, the one big exception here is helium. It's not going to have 8 electrons because remember, it really goes back here in terms of electron configuration. It only has 2 total electrons, so its configuration ends in S2. It's actually filled though. So some people call this an octet and a duet rule because it's a duet for hydrogen and helium. They're trying to get to, hydrogen's trying to get 2 total valence electrons to be like helium. Helium does have a filled outer shell because at the 1s level, at principal quantum level 1, all you can have is this maximum of 2 electrons, like helium, because there's no p at the first principal energy level. So helium acts like a noble gas because its filled outer shell is filled. It's just an exception to being 8. It doesn't need 8 electrons, it needs 2 to be happy. All the rest need 8. So hydrogen and helium are trying to meet that duet rule, and everybody else is trying to meet an octet rule. Okay, so this is pretty messy. I'm going to get rid of that. So octet rule is just an atom is stabilized by having its valence energy level full, right? It wants to be filled with 8 electrons, or 2 if it's hydrogen, to be like helium. Noble gases already fulfill the octet rule. By their very nature, they already have that outermost S and P filled with 2 and 6 of 8 electrons. Other atoms are going to gain or lose electrons to form positive or negative ions. They can also share electrons. So that typically happens here in the middle at 4 valence electrons. There's a lot of sharing of electrons to get filled outer shells there. So gain or loss of electrons to form ions, or sharing of electrons. Okay, next let's talk about ions. Ions are atoms that have gained or lost electrons to be charged, right? So they gain or lose electrons and adopt an electrical charge. If they have more or less electrons than protons, they're going to have an overall charge to that atom, and then they're going to be an ion. So metals form cations by losing electrons. Remember, I liked to remember that cations were positive with my kind of morbid looking little cat. And I just remember that cations are positively adorable. Oh, so cute. Positively cute. Okay, so main group cations have the same name as their neutral metal. So we're going to work with sodium. Sodium as an element is called sodium, and as an ion is called sodium. So let's find sodium on our table. When it has no charge, if we find sodium right here, it always has 11 protons. And when it's neutral and with no charge, it has 11 electrons. So let's write its electron configuration. 1s1, 1s2. Okay, 1s2. 2, so we're on level 2. We had 1s2. We're at 2s1 and 2. Then we're at 2p, and we go all the way and we fill the 2p to 6. And then we go down to the 3s1. Okay, so at 3s1, we don't have a filled octet. We just have one electron in that outer valence shell. Since sodium has only one electron in its outer valence shell, it's going to be easiest for it to lose this one electron, because then it will reveal a filled outer valence shell of 2s2, 2p6 below that. That's how sodium is going to form an ion. So let's write in our answer here. Our electron configuration was 1s2, 2s2, 2p6, 3s1. Na is sodium. Now, for the ion, it's going to lose that outermost electron. It's going to say, I lost an electron, I lost an electron. And we're going to ask it, are you sure, sodium? And it's going to say, I'm positive. And Na plus is still just called sodium, so we don't name it any different. Sometimes if we're really trying to clarify, we might say that it's a sodium ion. Okay, so what's more stable, the atom or the ion? Why? For sure, the ion, because of that full outer valence shell or octet. You know, it's meeting the octet rule, so it's for sure going to be more stable. With those alkali metals, we don't find them in their elemental state in nature. We find them out there as ions naturally occurring. Okay, so the charge on a main group cation can often be found by determining the group number, right? It's no surprise that sodium is in that first group 1A and has a +1 charge. So in the group 1A, they have a +1 charge, and in group 2A, a +2 charge, and in the aluminum +3. You know, others that we need to memorize or know are zinc with +2, and silver is a +1. So again, you know, sodium is going to be a lot more stable in this form. You know, when we hear about sodium in our diet or in everyday life, you know, it might be like, I had too much sodium today, or wow, there's a lot of sodium in this, you know, in these potato chips I'm eating or something. That's as sodium chloride, and that's as the ion form, because sodium, the element, is highly reactive, right? If you watch any of the alkali metals videos, it's highly reactive with water. And so we wouldn't be eating sodium, the element. So in our everyday lives, and when we refer to sodium, it's usually as the ion because that's a lot more stable. Okay, transition metals are pretty important. And, you know, if I'm honest, I think they're a little tricky, but we're going to have them down in no time. They can also form cations. So far we talked about the group 1 being +1, the group 2 having a +2 charge, and over here with aluminum, starting with aluminum, the metals below aluminum, because we know that boron is a semi-metal, you know, a +3 charge. Now, there's all these transition metals here in the middle, and a lot of the transition metals don't follow a simple pattern. And they could have a whole variety of charges, anywhere from +1 to +7. Oh my. Many of them form more than one charged ion or multiple charged ions. For example, here we've got chromium can be a 2 plus or a 3 plus. Manganese can be a 2 plus or a 3 plus. Iron can be a 2 plus or a 3 plus. Cobalt 2 plus, 3 plus, and copper +1 and +2. And then over here, we've got tin can be +2 or +4, and lead +2 or +4, which is interesting because it's in that fourth column. So there are some +4 ions in this fourth column. So that's kind of interesting. Not really a coincidence, right? But definitely due to their placement on the table. So transition metal cations have the same number as the neutral metal with the charge in Roman numerals in parentheses. So same name as the neutral metal, and then they've got a charge in Roman numerals in parentheses. So it is helpful to know our Roman numerals here. So when we mean 1, we just put an I or a 1 in parentheses, and sometimes it'll look like a capital I. And when we mean 2, I almost started just writing the Roman numeral. We write a Roman numeral 2 with these 2 lines in parentheses or 2 capital I's. So sometimes they have lines like that. And 3 would just look like 3 lines, or it might look like that. And then a 4 is interesting. It's helpful to know 5. We don't do too many 5s for charges, but 5 is actually a V, and that V could look like this. 4 is actually a 1 in front of the V, because the idea is you take 5 minus 1 is 4. So we will see that, 4 a fair amount, because we said we're going to use 4. Okay, so name the following cations. So why don't you pause, get out your periodic table, and find the names of these ions. Did you hit pause? If you didn't yet, because you weren't sure, I'll help you out with a couple. Okay, calcium is right here in the alkaline earth metals. So all we have to do is put the name calcium. It doesn't have more than 1 charge. It's always +2 because of its location. I'll do a trickier one. What about cobalt? Cobalt is found over here in the transition metals. It can have more than 1 charge. So we have to say cobalt, and then we have to put its charge in Roman numerals. So a 4 is I minus 5, right? And we can put lines across the top if we want, but that's our Roman numeral 4 for cobalt 4. Now you could hit pause and try the last 4. Okay, so potassium's a group 1 element, so all we have to do is name it potassium because it only ever has 1 charge. Now, zinc, I was going to mark where zinc was for you already, and I don't think that I have. All right, well, I'm going to mark silver right here as a plus, or +1, but sometimes we don't put the 1. Chemists drop the 1 a lot. We're lazy with that 1. And we should have zinc right here, and zinc would be a 2 plus all the time. Oh, and then aluminum is always a +3 or 3 plus. Gosh, I didn't really have enough room for that. But aluminum's 3 plus goes right here. So it's worth writing a +1, a +2, and a +3. And if you didn't fit them very well with their names in there, you could just write the charge, +1, and +2, and +3. Here, I'll show you that again. Plus, 2 plus, and then aluminum, 3 plus in this box for aluminum. Okay, so here's the thing. Zinc might be in those transition metals, but zinc always has a 2 plus charge, so we don't actually have to put its charge in parentheses because we know it's a 2 plus. Chromium now, I've even shown you right here. Oh, reminder, it can have more than 1 charge. It can be chromium 2 plus or 3 plus. So we're going to write that out with Roman numerals. We're going to write chromium 2, and then we're going to write chromium, and then a Roman numeral 3. Perfect. Okay, so that's metals, like group 1 and 2 metals, and the metals we know, like silver, zinc, and aluminum, and our, our other transition metals. Okay, I want to stop right here and rewrite those important metals. Right here we have silver, always a +1. We have zinc, always a +2. Then we have aluminum, always a +3, right here. So I would go ahead and write those on your table so that you have them. Again, +1, +2, and +3. Just so they're always there for you because those are charges we know for certain. Okay, nonmetals can also form anions. They have a negative charge once they've gained some electrons. Anions are named by changing their ending to "ide." So let's do a practice with phosphorus. Let's find phosphorus on our table. So it's here with atomic number 15. Phosphorus always has 15 protons. That's what makes it phosphorus, but it will also have 15 electrons if it's neutral. Okay, so let's write its electron configuration. We've got 1s2 and then 2s2. And then here we've got filled the 2p6, and then we'll fill the 3s2. And then we'll fill the 3p to 1, 2, 3 electrons. 3p3. Okay. So the electron configuration of phosphorus we've got right here. So I'm not going to rewrite it because it's pretty close in proximity. And we're just going to call it phosphorus as the element. Okay. So, OUS. Jeez. Okay. Ha. OUS. And the electron configuration of the ion. Well, here's the deal. Phosphorus right now has 3s2, 3p3. It has 5 of its 8 valence electrons. If it's got 5, it only needs 3 more valence electrons to get to 8. It's going to be better for it to gain the 3 more electrons it needs to get to 8 than try to lose all 5 of these. So it's going to gain the last 3 that it needs right here. So if it gains 3 electrons, it will have 18 electrons. That's what makes it 3 minus, because it has 3 more electrons than it does protons. Okay, so we're going to change its electron configuration. We keep all of the core, 1s2, 2s2, 2p6. Core was all filled. Get to the valence, 3s2 is fine, but 3p needs 3 more, or 3p6. And to name this, we actually do change the ending to phosphide. So we change that phosphorus ending to phosphide. What's more stable? Again, the ion. Why? Again, that full, outer valence shell, that filled octet. It wants to have that full octet and to be like a noble gas because they're not very reactive. Noble gases aren't very reactive. Ions that are like noble gases are also going to be filled and less reactive. Okay, so let's clean that up because that's just too hard to read or look at. The charge of the anions can usually be found by their group number. We know that the noble gases don't form any, they're full. So here we've got a -1 in group 7A, -2 for the nonmetals in group 6A, and -3 for those here in 5A. Now notice we're just putting that for the nonmetals. So, we had our staircase here, and so we're not really doing that for our semi-metals. And there's even some of our nonmetals, like for example, carbon here, that are not going to act this way, that are going to share electrons and not really form ions at all. So for the ones that form ions, it's pretty easy. It's -1, -2, and -3. So -3, -2, -1 for those groups. Okay, so it says practice. Let's name the following ions. So nitrogen as an ion, we change nitrogen to nitride. So we're cutting off the ending and changing it to "ide." Do you want to try these two? Press pause. Okay, oxygen here we can change to oxide. And then bromine here we can change to bromide. All right. So that's how nonmetals gain electrons to form ions. The last thing we need to cover in terms of understanding ions are what are called polyatomic ions. So poly means more than one. Atomic really is just like it sounds. It's about atom. So we're talking about more than one atom. And what are ions? Well, those are atoms with a charge, right? More than one atom with a charge. So these are multiple atoms put together and they have a charge. More than one atom with a charge. Groups of atoms with a single charge. There's 10 of them that we really need to know. But there is a good way to remember them. So the way that we remember these oxoanions, oxo 4, they have oxygen. So they have oxygen, they're anions, so they're negative, polyatomic ions. So they're negative, and they have oxygen. Is with this little trick. It's Nick the camel ate a clam for supper in Phoenix. I like the 4. Clam for supper in Phoenix. The important words are the big ones. Nick, camel, clam, supper, Phoenix. So the longest words in the sentence are the important big ones. So here's the deal. It's a little bit goofy, but here's how Nick the camel works. Let me give myself some room. In Nick the camel, the number of consonants in the word tells you the number of oxygens you're going to put with the first letter of the name. And then the number of vowels in the word tells you the charge of that ion. Like what the negative charge is going to be, like -1 or -2. Now remember, vowels are A, E, I, O, and U. So consonants are all the other letters, right? Here's how it works. You go to Nick the camel. You go, okay, N, C, and K are consonants. What's the formula? I'm going to start with the N. The consonants tell me the number of oxygens. How many oxygens? 3. There was one vowel, the I, so it's going to have a charge of negative or -1. We're lazy as chemists. We don't often write the 1. Okay, then we have camel, an ion starting with the letter C. Camel has 1, 2, 3 consonants, so there will be 3 oxygens. Camel has 1, 2 vowels, and its charge is 2 minus. How about clam? Clam, we have to use the C and the L because we've already made an ion with just carbon. So this is an ion with chlorine. Okay, but we still stick to our rule. We go to clam and we go clam has 1, 2, 3 consonants. C, L, and M are consonants. So we're going to have 3 oxygens. And A is 1 vowel, so it's going to be negative. ClO3 minus. Supper. Okay, so we have one starting with S. Supper has 1, 2, 3, 4 consonants. This ion's SO4. Supper has 2 vowels, U and E, so it's going to be a 2 minus charge. And then we get to Phoenix. That's an ion starting with P. Phoenix has 1, 2. Well, yeah, your first issue is spelling Phoenix, I think, so I have to know how to spell that to kind of practice that. P-H-O-E-N-I-X. Okay, so P-H, N, and X are all consonants, so we'll do 4 oxygens. And then O and E and I are all vowels, so we'll do a 3 minus, or a -3. So hopefully that can help you with these 5 ions. What are the other ions we need to know? Ammonium is really important, NH4+. That's the only really cation positive. Let's note that ammonium is a cation. It's really the only positive polyatomic ion that we need to know here. Cyanide is Cn-. You might have heard of things that contain cyanide as typically being poisons. Facts. True. Okay, so carbonate Bicarbonate is a lot like carbonate. It's carbonate that's got a hydrogen in front of it, HCO3, and having that H essentially neutralizes one of the negative charges, so it's only a -1, HCO3 minus. Hydroxide comes up all the time. It's OH minus. Its name kind of sounds like the H should come first and then the O, so you have to flip them. OH minus. And then we have our acetate ion, C2H3 O2 minus. Notice how down here all the charges are just 1, right? So most of them are -1 except ammonium, that's a +1. Okay, so let's just do a little bit of practice. We're going to practice naming these ions. Why don't you pause and see if you can name the ions. All right, ready to try them with me? Magnesium is a group 2 metal, so we can just call it magnesium. CO3 2 minus, we just learned was one of our polyatomic ions to know, and that one is carbonate. Li plus, group 1 metal, so we can just call it lithium. Chlorine, non-metal, so we end it in chloride. So the ide really indicates usually that you just have an element. So ide is for element. There are those 2 main exceptions that we just saw. Cn minus, of course, is cyanide, and OH minus is hydroxide. Usually, ide tells us we have the element, unless it's cyanide or hydroxide. Usually, ates and ites tell us that we have polyatomic ions. Okay, here we've got iron, and iron can have more than one charge, and this one is iron 2, because here we have iron 3. If I hadn't shown you both irons to tip you off, you would really double check that you have a main group metal or a metal like aluminum or zinc or aluminum, zinc, or silver that we know before, busting out your Roman numerals for a transition metal. Okay, here we have sulfur, but sulfur is a nonmetal, so it changes to sulfide. And then this is an important one we need to know, ammonium. Okay, so this concludes our discussion of valence electrons and ions, getting us ready for bonding and nomenclature, bonding and naming.